Right, so in this topic, we talked about 3 different ways to solve for new initial concentration, but no equilibrium concentrations. So that's the x is small, the perfect square, and the quadratic way. But what we also talked about at the end was the fact that if you were given one equilibrium concentration, you could apply that to all of them. Essentially, you're given x. And so you don't have to go through the quadratic math uh, or the x is small to solve for x. You're given x by knowing one concentration at the end. So this one's a little more complex in that we have to fill out all the missing information. And so the process is a little bit more complex, but the solving for x is more straightforward. So first thing we have to do, we're given moles, not molarity. But if we look at it, we see it's a 1 liter solution or a 1 liter vessel. And so all these moles are actually equivalent to molarity because they're just divided by 1. So let's see what we're told here. So initial concentration of SO2 was 2 molar, 2 divided by 1, 2 molar for NO2, and they're allowed to react at high temperature. And then there was 0.13 molar of NO in the vessel at equilibrium. So let's put some of these in. Okay, so 2 molar SO2 to start. We also had 2 molar NO2. And then there were 1.3 moles of NO at equilibrium. So that's what we know. So we didn't have any of the products when we first started. So we're gonna know that this SO3 is a plus X. It's 1 to 1 to 1 to 1. So this will be plus X. This will be minus X. This will be minus X. And then, so this will be 2.0 minus X. And this will be X, and this will be X. And this is 0. Okay, so we have enough. So the fact that we know that this is X and it's 1.3, X is equal to 1.3. So we can actually put those in all these spots. And the only math we really need to do, so this will be 1.3, this will be 1.3, 1.3, this will be minus 1.3. And so all we have to do is 2 minus 1.3, which is 0.7. So these will be 0.7s. So we can put all these in. So we'll have 0 here, 0 here. Now this thing here, you can use if you have like a solid or a pure liquid, you would just not include it. So that's why that's there. So we got a minus 1.3. And then we have 0.7s. And we have a 1.3 here. Okay, so there's all our minus x's. 2 minus 1.3 is 0.7, x, x. But we do have a next. So the next is based on the setup of your ice table, construct the expression for Kc. Now remember, Kc is equal to products over reactants. They're all 1-to-1, so there's no squared. And what we saw was both these were 1.3s, these were 0.7s. So that's what our expression should look like. Now it says, do not combine or simplify terms. So that means don't multiply 1.3 times 1.3 and just put one number on top. So put them each separately. Now I do the math. So essentially 1.3 squared divided by 0.7 squared, and you get 3.4. Okay. So that, and then you can go back to here and also see this is correct. In this case, we had a 1 to 1 to 1 to 1, which made it a little simpler. The key with these is to build this table out and understand what is x. And so in this case, x was equal to 1.3, and we were able to apply that here, 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 and not have to do a Ka equals x squared type of equation. But keep track of these 1 to 1 to 1 and make sure you don't, if you have any 2s or 3s, you're going to have to, when you get to this table, make sure you have that squared in there or whatever it might be.